Struggling to decode those MCS 305 lecture notes? Well, welcome to this explainer. We're going to crack the code of the MCS 305 exam by transforming all that complex material into your ultimate visual study guide. If you've been staring at pages of text, just trying to memorize micro operations and addressing modes, you are absolutely in the right place. We're going to make this highly visual, incredibly structured, and super efficient. Let's get right into it. We're kicking things off with a direct pop quiz straight from question 1C of your exam doc to set the stakes. Understanding the CPU as the brain that executes instructions, well, that's the foundation for everything else. So what's the exact function of a microprocessor? It acts as the central processing unit on a single integrated circuit chip. It reads instructions from memory, performs calculations, and coordinates all the other components. It is literally the heartbeat of the machine. Okay, here's our roadmap for today. First, the big picture. Second, the 8085 architecture and registers. Third, instructions and addressing modes. And finally, register transfers and microoperations. Section 1. The big picture. Understanding microcomputers versus microprocessors. We're going to tackle question 1 head-on by looking at the broader system. You really have to know the difference between the processor itself and the computer it sits inside. To answer question 1A, take a look at how the microcomputer breaks down into distinct blocks. You've got the microprocessor, or CPU, on the left, which connects via system buses to your RAM and ROM memory, your I/O ports, and your peripherals. Just think of these lines as highways of information. Honestly, if you can sketch out this simple box and line setup, you've just secured 10 marks. Moving right along to Section 2. 8085 architecture and registers, the internal hardware. Now we're zooming in from the overall microcomputer to the microprocessor itself to knock out questions 3 and 7. We're going straight inside the chip. If you're asked to draw the 8085 architecture for question 7A, knowing this layout is your golden ticket. It clearly maps out the arithmetic logic unit, the various registers like B, C, D, E, H, and L, the instruction decoder, and the timing controls. Now, I know it looks incredibly complex at first glance, but really, it's just a mapped-out flow of how data moves from external buses into temporary storage, gets processed in the ALU, and then gets pushed right back out. Let's rapid-fire through the definitions you need for question 3A, starting with registers. Think of registers as the CPU's quick access scratchpad. Instead of going all the way to external RAM, which takes a lot of time, the processor keeps the data it needs right this second in these small, lightning-fast memory locations. Next up in question 3A is the accumulator. This is the true workhorse, or rather the grand central station of the 8085 microprocessor. Whenever the arithmetic logic unit performs addition, subtraction, or logical comparisons, the accumulator is where one of the initial operands comes from. And, most importantly, it's almost always where the final answer is deposited. Then we have the program counter. Think of this one like a bookmark in a really long novel, constantly keeping your place so the processor knows exactly what line of code to read next. Because it holds a memory address and the 8085 uses a 16-bit address bus, the program counter itself absolutely must be a 16-bit register. Similarly, the stack pointer is another 16-bit register. Just picture a stack of plates at a buffet. It tracks the top plate so you know exactly where to pull from next. It's crucial for managing temporary memory, keeping track of where the most recently pushed data resides in your stack. Whenever your program jumps to a subroutine, it uses the stack pointer to remember where it left off, so it can return safely. Pretty neat, right? Finally, to finish off question 3A, the instruction decoder. This acts as the universal translator of the CPU. The processor fetches an operation code, or opcode, from memory in binary. The instruction decoder takes that binary code, figures out what it actually means, like add or move, and then generates the actionable physical control signals inside the chip to make it happen. All right, Section 3, Instructions and Addressing Modes, Commanding the Hardware. With the hardware fully defined, we're moving to our third section to understand how we actually command this machine. This specifically answers questions 2, 4, and 5. This right here is where software meets hardware. Question 2A asks for the 5 groups of 8085 instructions, and they are perfectly categorized for you. You literally just need to list data transfer operations, arithmetic operations, logic operations, branch operations, and machine control operations. It is really that simple. These 5 categories cover everything from moving bytes around to jumping to completely different parts of your code. To nail down question 5a, which asks about addressing modes, we can see side by side how instruction formats directly dictate these modes. Addressing is just the process of specifying the data to be operated on. You have immediate addressing, where the actual data is right there in the instruction, and memory direct addressing, where the instruction simply gives you the exact address to go find the data. Now, question 3c asks specifically for an example of indirect addressing. In this mode, a register pair, like the H and L registers, acts as a pointer to the actual memory location. So the register isn't holding the data, it's holding a map to the data. That's indirect addressing. An instruction like move A, M means move the data into the accumulator. But where's the data? Well, it's in the memory location whose address is currently sitting inside the H and L registers. Section 4, Register, Transfers, and Microoperations, the microscopic mechanics. For our final section, we're diving into the exact mechanical sequence of data movement to easily conquer questions 5 and 6. This is the true microscopic level of computing. Answering question 5b starts right here with Register Transfer Language, or RTL. RTL is a symbolic language and a super convenient tool used to describe the microscopic clock-by-clock operations of the computer. It's how we express the internal hardware organization by specifying the precise sequence of microoperations performed on binary information. The second half of question 5b asks for a conditional transfer example. You write it as P:(R2 arrow R1. And what does that mean? It simply means the transfer of data from register 1 to register 2 only occurs if the binary condition P is equal to 1. If P is 0, nothing happens. It's the fundamental logic gate of data movement. Now, if question 6c throws you off by asking for the steps to write into memory, don't panic. Just memorize this straightforward 1, 2, 3 sequence. Step 1, load the address register with your target memory address. Step 2, load the data register with the actual data you want to save. And step 3, trigger the memory write operation so the data flows straight into that specific location. To solve the arithmetic shift problem in question 6a, we've got to remember the basic rules. An arithmetic left shift multiplies a signed number by 2, while an arithmetic right shift divides it by 2. The absolutely crucial point for a right shift is that you preserve the sign bit, the leftmost bit, so the number keeps its positive or negative value. Let's work through question 6a together. Our initial 8-bit register holds 01010011. Shifting the bits arithmetically to the left, we drop the far left 0, shift everything over, and add a 0 to the right. That gives us 101100110. For the arithmetic right shift, we move everything to the right, but we duplicate that original sign bit, which was 0. So we end up with 00101001. Boom, problem solved. Let's do a quick recap of exactly how data moves between the data register and memory via the address register. You've done the hard work, and this is the payoff. When we read, the data flows from the memory at the address specified by AR straight into the data register. When we write, it flows from the data register back into that memory location. As you go ace your MCS 5305 exam, ask yourself this: how do the basic microoperations, addressing modes, and registers we just decoded currently scale up to drive the most advanced AI supercomputers on Earth? The computing speed of an 8085 was measured in megahertz. Well, today's chips are billions of times faster. Yet, the core logic hasn't changed. It's just gotten infinitely faster and wider. Keep that in mind